Welcome everyone. Thank you for coming to this talk. My name is Etienne. I'm from Montreal. I'm an Android GDE. I'm an Android GDG organizer, so I like a lot of Android-related things, as you can guess. And I'm actually pretty passionate about VR. So this story kind of started when we went to a hackathon in San Francisco after I/O for VR at the Adobe offices. You have to play around with Tango and like different the Rovis dive helmets for the Tango, and it was quite fascinating. So I started basically thinking, well, I have to start making apps for this thing. This is interesting. I want to make apps for cardboard, you know, right? Greater coverage for people. Thing is, when you start making a cardboard app, and I wanted to do it with Java, because I like challenges that way, I had a lot to learn. I didn't actually know all that much about OpenGL. I mucked about with it like ever since the 90s, but it kept changing. You know, I'm a bit lost with what was going on. So, you know, things kept breaking every time I changed a small detail, so that was really painful. So not being a very sensible person, I've been doing this since last May, and I'd like to share with you some of the things I've found out and some of the pitfalls you could possibly avoid. All right, so we have a few sections here. So this one's about OpenGL theory. So to be aware of the ecosystem, you have OpenGL, which is for desktops, and you have something called OpenGL ES, which is for mobile. Out there right now, OpenGL ES1 is sort of non-existent anymore. It's what you had on the first versions of the devices. They had a non-programmable pipeline. So I'm going to be saying programmable pipeline a lot during this talk, just fair warning. With ES2, it brought the programmable pipeline to the mobile world, and this was a good thing. So now we're in 2015, thank you. And we have OpenGL ES 3.1 and something called the Android extension packs. So these add a ton of features. So you get compute shaders, stencil textures, accelerated visual effects, high quality ETC2, EAC texture compression, advanced texture rendering, standardized texture size, render buffer formats, more and more and more. And the Android extension packs allow us to do things like this when you're looking at an Android device such as Android TVs, which might be running you know, very powerful hardware. So these extension packs you install on a specific device, and if the device's hardware supports it, you get almost desktop equivalent performance. So this was introduced at I/O, I think 2014 actually, and it's based on the Unreal Engine 5, right? And for the future, we're going to have something coming up called Vulkan. So Vulkan was announced this summer. It's a new initiative. If you've heard of Apple's Metal for iOS, it's fairly similar. So the idea is that you're even closer to the GPU. They strip away parts of the framework that would make things theoretically easier for you. This will likely lead to more complex apps, but for developers, it will give them far greater control. So we still have to see a bit more about that. It's just been announced. It's not really, I haven't seen any specs yet. So I think it's being worked on currently at various you know, manufacturer offices and things like that. So you might be a bit dizzy at this point because of all the alphabet soup and acronyms I've been throwing around. And that is normal. The key takeaways from the previous slide are plain OpenGL is for desktop. ES is for mobile devices. ES2 is where you started getting the programmable pipeline. ES 3.1 is what we'll be looking at today. Things to keep in mind, it's supported, say, on a Nexus 5. It's supported since Lollipop, but some phones won't support it due to limited hardware on these phones. So you're going to need to programmatically check if you get into a production kind of scenario. Yeah, so let's look at core OpenGL concepts we're going to be playing around with today. So we're going to go for minimum effective dose, right? I'm going to try to gloss over a lot of stuff because we only have so much time. And yeah, time is precious, right? Right, so we're going to look at geometry, math, and core 3D concepts. And my idea is that not a lot of people here in the audience have a lot of previous experience with OpenGL. So I'm actually going to ask this right now. Who here has actually wrote an app using OpenGL ES2 or 3? Right, so a few people, good. Like share notes with the others if they look confused. Core concepts. We're going to be talking about 3D space. So you're probably familiar with the idea of Euclidean space, right? X, Y, and Z. I had the honor of choosing a graph where the axes are sort of wrong for OpenGL. So just to clarify something on OpenGL, this is X. this is y, and z is depth, right? So, right. Then we're going to be talking about the vertex a lot, or something called vertices, plural. The thing to note, though, which might be a bit confusing, is that we're going to be talking of the vertex, of course, as points in, say, an object, right, as part of like a triangle that composes the faces of the object that we're going to render. But we're also going to be talking about attributes hooked to that vertex. So it's not like the pure math vertex that we're used to talk about. It will have other concepts associated to it, like normals, color, things like that. Vertices assemble into primitives. This is like really the old school graph from like the Red Book, OpenGL Red Book from the 90s, or even earlier probably. The one we're going to be playing with a lot is triangles. To make a distinction between triangles and triangle strips or fans or all these other things, you might be wondering, why is this even in the spec? Just a quick, we're going to be talking about performance a little bit. One of the things with OpenGL is that the more data you have to shove into the pipeline, the slower it gets. So you might notice here that a triangle strip, for example, uses up less vertices than a plain old series of triangles, right? Because they share vertices. So let's talk about models. So these are wireframe models. As probably a lot of you know, models are actually usually, well, in this case, we're going to be talking about triangles as our primitive. So all these models will be composed of vertices that form triangles that form the model, right? The important point I want to make with this slide is that when you create a model, say we are going to talk about a cube, the coordinates of the vertices are going to be around the 0, 0, 0 origin, right? So everything is always going to be relative to the origin, more for management reasons, as we'll see a bit later. So another concept you have to sort of get your head around is transforms. So we're talking about translations, moving an object in a different point in space, rotations, twisting an object, and scaling is also one, making things bigger or smaller. What you might want to note from this slide is that the order that you apply operations is important. The good news here is that the example code that comes with the talk, all this has been taken care of for you. You don't have to experiment and sort of go, oh, why is this moving all around so wrong? And I'm confused. So a lot of that will be taken away, which is good when you want to experiment. Just to keep that in mind when you're going to get a bit deeper into the rabbit hole. All right, linear algebra, right? Transforms imply matrices, multiplication of matrices. So most people, their math courses are far away, and these are fuzzy concepts, and you don't want to mess around too much with that. The good news is that this is all taken care of mostly by the SDKs and the APIs, so you don't need to worry too much about it. You do need to understand that all the operations I've talked about usually end up in one big matrix, and you multiply your vertex by that matrix, and the vertex will be placed into its proper space, its proper coordinate space. We'll come back to that. All right, another big concept. So projections and cameras. Right, so when we're going to configure our OpenGL pipeline, we're going to have to set up rules of projection, right? So if you look at the first figure, the idea is we're telling GL how to project things. So it involves telling it what are the bounds of our view, the top, the bottom, the left, and the right. And also involves giving it some configuration so it kind of knows what is far and what is close. So when it comes time to project the vertices we have in 3D space onto our 2D screen or our 2D rendering area, it'll know how to sort of proportion these things, right? So this is through configuring that. That, again, don't get too worried about it. You'll see that line of code. You probably won't even notice it. It's a one-liner, but it's a fairly simple thing. But you need to be aware of all this theory to sort of fix things when they start going wrong. The other diagram is just here to illustrate that we also need to place our models, but we also need to put the camera in there, right? So we have the concept of objects in space projected onto a screen, but we also have the concept of this camera that's moving about and looking at things. So that's also an important thing to remember, because that's going to be another mathematical operation that we're going to sort of shovel a bit under the carpet, but that's going to be there and that you'll want to be aware of. All right, so lighting. Lighting is super exciting. So we'll learn how to implement Lambertian reflectance. Lambertian reflectance is named after Johann Heinrich Lambert, who introduced the concept of perfect diffusion in his 1760 book Photometria. Now, I actually have a few scans from an early edition. Yeah, all right, let's start that over. My lame attempt at a joke today. Simple lighting, right? We want to keep things simple, and lighting, to be sure, is actually a super important subject in OpenGL, and it gets gnarly very quickly. So we want to avoid that for today. We just want to have like the base minimum lighting model that we can use to sort of start experimenting. So we do need to understand two concepts again. Ambient lighting, which is just the light that reaches an object after bouncing around everywhere in the room. So it's sort of your background radiation lighting. It's the minimum amount of light that a point on a surface is going to get by default. And then you have something called diffuse lighting we'll be playing with, which is the light that reaches your eye after a source of light, sort of the rays bounce off a surface and reach your eye, right? So here the amount of light reaching your eye will be sort of directly proportional to the angle between the surface of the object and the source of light. And that's what this whole Lambert cosine law is going to be about, which we're going to see in a few frames. But it's, again, very easy to calculate all that stuff with OpenGL. It's just, right now I'm giving you context, so when you see that line in code, you'll be like, oh yeah, it's that thing he talked about earlier. All right, another important concept related to lighting is normals. So a normal is a perpendicular vector pointing straight out of a face, or of a facet of a shape, right? But in our case, we're going to have normals associated to vertices, right? And that's slightly different because if you look at the last diagram here, we're seeing normals coming out of a bent shape. So what happens is that you can sort of make approximations with normals where even if you are actually playing with a triangle, that triangle is part of a sphere, right? You could make it so that the normals are sort of pointing out from the center of the sphere. So that helps the lighting model light this thing as if it was a sphere and help you get a better simulation of these shapes and everything. So the other thing I want to quickly say is that normals, so you might all know this already, but it's worth mentioning that normals are called normals because they are normalized vectors, meaning that they have one unit length. So you might remember that from one of your old, well, in my case, old math courses. So just to make it a little reference. All right, so we've talked about vertices and how in OpenGL they're actually a combination of things. So in this case, I just wanted to show quickly that you have basically, we're going to have position, the normal, the color, and texture we're not going to play around with today, but these are like all attributes that are hooked up with this bundle of data that is a vertex in our pipeline. And on the right side, I just wanted to point out and sort of give you a hint that if you've never done GLSL before, how that language looks like. GLSL stands for Graphic Language Shading, no wait, GL Shading Language, which is kind of redundant. Maybe it's Graphic Library Shading Language rather, so it's not redundant at all. All right. So just be aware of the VEC3, VEC4, and VEC2. That really represents an array of floats in this case, all right, just so you know. All right, one of the few last complicated gnarly diagrams I'm going to show today, I'm not actually going to go over this. I just wanted to point out if you go to the Chronos site, you can get the full picture of what is the OpenGL pipeline in big detail for 3.1. It's actually good reading once you've gotten familiar with the basic concepts and you want to start playing around configuring your own setup. But let's skip over that right now and look at it at a very high level view. You can think of the OpenGL pipeline as a client-server relationship, a very simple one at that. You have your application, which is running off of the CPU, right? Talking to the OpenGL ES framework client, which is also running off of the CPU. And you're talking to this to configure this whole pipeline, right? You're going to be feeding data in there, and that's all happening on the CPU, and CPU land is kind of slow. And the transfer from CPU land to GPU land is almost equivalent to a web call. So that's really the key idea with this frame, the slide that you should sort of take away. Right. The other thing is like I had to have a perf matter slide. It has nothing to do with enums. I couldn't find a way to shove it in there. But this magic number, 0.016 milliseconds in this case, if your rendering goes over that, you're going to make your users nauseous, especially since we're not talking about the Vive here, right? We're talking about cardboard on phones, which might not be all that great. So you're going to need to start thinking about performance pretty early in the process. So the better way of doing this, you'll see that we have it in our examples, is to have a frame rate indicator that you can keep an eye on, so that when you're experimenting, if ever you see that frame rate drop dramatically under 60 frames a second, which you can't go over anyway, right, because the refresh rate of the device is pretty much 60 frames a second. But when you start dropping those frames, you have to ask yourself, okay, I should start being careful, right? Like I should probably change my approach, read a few optimization articles, and start fixing it. So early optimization I'm not super fond of, as most people aren't, but early warning signs, that's pretty good. All right, so the simplified graph for the OpenGL pipeline. The thing to note here, the color code. So the blue is mostly happening in user space, right? It's happening in your app in Java. So that's where you're going to take all these vertices that you got from somewhere, shove them into the pipeline. That's where you're going to configure the pipeline and actually pass it the programs that it's going to execute at different steps. This is where most of the Java code you're doing is happening. After that, the vertex step is one of the first programmable stages that you're going to give a program to the pipeline to execute. This thing is running over each of the vertices being fed into the pipeline. I know it's very theoretical right now, but hopefully it'll start coming together in a few slides. I just want to get good basics. So those vertices, right, you're going to be calculating on them, and you're going to be sort of basically projecting them onto the screen, which will allow then that the green part, so the yellow parts are programmable stages. Green part are fixed stages. You don't get to program them. They're part of the OpenGL framework. And in this case, what's going to happen is going to take the vertex data, and it's going to decide, OK, so where on screen are these primitives? So it's going to map those out. And once this is known, it goes on to the fragment stage, the other programmable stage. Fragments are basically programs that are there to paint a pixel. So for each of the pixels you have on screen, the fragment shader is going to run once. So we'll see how we can do a lot of fun stuff with that later. Finish up the chain, their frame buffer. It's just there to sort of give you the hint that you can make a lot more complex builds with the OpenGL pipeline, but you don't need to. You can basically see these two steps and up to the GL surface view as I'm dumping a bitmap to the screen. All right, so this slide is to reinforce the idea, which I don't find is very intuitive for most people, that you first have vertices that are being computed on, which are sort of projected onto a screen. And once that sort of relationship between the model in space and the actual screen is done, then each of these pixels, the system knows which shape they belong to. So it now knows what computations to accomplish and what parameters to pass to your program for it to calculate the color of that pixel. A small slide on the power of parallel processing. So what we're looking at here is, I couldn't find a good video of it, sadly. It's an NVIDIA event where the Mythbusters were there to actually sort of show why is parallel processing much more awesome than linear processing or a CPU. So all they had set up is a paintball gun that was drawing the Mona Lisa. So they had the first one instance at a time. The robot arm would paint a wall with paintball pellets, which was kind of cool. And then they had a massive array representing GPUs, a lot of them, running on NVIDIA hardware, presumably, painting a picture really quickly, right? So that's the other thing to think about, is that if that program's running for each and every pixel in your frame, it's actually all running in parallel, which is how this can be actually a fast process. OK, so some practice, some actual code. Get ready. It's going to be heavy. Maybe not that much. But anyway, we're going to start with vanilla Android OpenGL. So again, we have a few people who've played around with at least OpenGL. So you're going to be familiar with this. I'm going to sell the punchline a little bit. You'll see that with Cardboard, you don't need to add that much code to what you've already learned to actually get a VR app running, which is the good news. So this class diagram, the takeaways here, GL surface view, it's an actual view. It inherits from the view. And the thing that actually draws to that view is a renderer. So that's a subclass of GL surface view. You are the person that will implement that. It's more of an interface or an abstract class. I'm not sure. I should have checked. I will for the next talk. But basically, you're going to be implementing on surface created, on surface changed, maybe. Most of the time, mine is empty, and on draw frame. So the action all happens in the surface created and draw frame. Surface created to initialize this whole big pipeline we've been talking about. Draw frame just to take the data that needs to be in the pipeline for now, shove it down there, press draw. We're done. All right. Threading, quick note on threading. I made this nice little diagram, and I want to really go quickly over it, though. So it's on its own render thread. The renderer is running on its own render thread. It's got its own dedicated GL rendering thread. So you have the same kind of challenges that you have with the UI thread. If you want to communicate with your renderer, you need to go through something like QEventRunnable or some other threading mechanism, okay? And this is so that you can get like reliable draw calls at all, your 60 frames per second. All right. Cardboard SDK, I promised it wouldn't be much more difficult. It's not. There are, however, a few new methods in the stereo renderer, which is the equivalent of the renderer we just looked at. So you have a few more calls that come into play when Cardboard is there, and we'll see which those are in a few seconds. You might notice at the bottom here that we are still using jars in the libs folder. Yay. Somebody talk to that team and get them on Gradle. Thank you. So setting up the GL pipeline, the first step that we quickly glossed over in the renderer. So onSurface created is being called with an EGL config. I'll say it right up front. This might be called more than once during the lifetime of your program if you get called and etc. Right? So you have to be ready to sort of think about reinitializing everything. That being said, the steps here, most of the complexity of the steps is abstracted in a class I call geometry, which you can see in my actual sample code that's available on my GitHub with a link at the end of the talk. I just wanted to give you the basics so you get started. So init buffers, yeah, so that's step one. Then step two is going to be init GL program. So those yellow steps in the pipeline, we're going to configure those after setting up the buffers. And then after we've set up the programs, we're going to initialize handles. So let's look each of those steps and break them down, what they actually do. Right, step one, initializing buffers. This is basically initializing a chunk of memory so that we can shove floats in there that will be our vertices and our vertex attributes, all bundled in there, so that we can then pass it to the pipeline. So as you can see, it's fairly straightforward code. Not much to say here, except you're sort of almost in C land, but that's okay. You're going to have to get used to it with OpenGL a bit. It's not that complicated, right? So step 2.1, initializing the GL program. I even bothered putting this here just to remind you that we're talking about the yellow stages, programmable stage of the pipeline, and that to mention that vertex shader code and fragment shader code are actually big string blobs. They're actually the source code. That's what we're passing in there. And so yeah, we won't dig into the load shader method that you see at the top because it's pretty much the same process as what's happening below here. So the first thing you do is you call a GL. So notice they're all like static method calls. Like every time you interact with the pipeline, it's that kind of call. In this case, we're using GLE ES30. You might have been using 20 before or whatever. So the number changes depending on features that you're using. So we're creating a program and we're getting a handle to a program. So we're basically telling the pipeline, create a program object for me. And then it's giving us back a pointer, pretty much. Then we can we've used the same kind of process to create handles to vertex shader and fragment shader up top, right? So at that point, we take those two handles that have been initialized in the pipeline, and we pass those two shaders into the program to finish with a link call. So the fun part, and we'll see that later, is that when you do this, you're going to actually get feedback from OpenGL as to whether or not you have compile errors, and they're going to be a bit verbose. So that's going to be interesting in a few slides. All right, so step 3. So I've talked about the handles, right? So this is how you get them. Literally give the string that's going to be well, we'll see in the shader, that's the actual variable name. So it's through a string. Might seem a bit clumsy of a way, but yeah. All right, so this is our first shader, the vertex shader. It's not, well, it's a fairly simple semi-pass-through vertex shader. So this means that we're not doing much here except transforming our current vertex into its final position, as I've talked about earlier, right? So we apply model, view, and projection transformations that are stored in this matrix. So one matrix can be a bundle of transformation that you can apply in one shot, and that's what we're doing here, right? So that lets us know where that vertex is going to end up on screen. For the fragment shader, it's going to come along afterwards to get its list of pixels, right? So yeah, while we're here, these are, so yeah, we have to mention these are the inputs that we just used in our Java code. So I just want to point those out, right? So you make a direct mental link between the two. And the outputs are kind of important. And this syntax is actually slightly different than ES2 for people who've done ES2 before. Like in and out, I don't believe we're in GLES2. So it's good to note these things because your old things might break if you start doing 3.1 or 3. All right, and the output basically are things that are going to be passed on, varyings that are going to be passed on to the fragment shader. So varyings, well, I won't get into that concept right now, but we can talk about it later if you're interested, maybe after the talk. All right, so last big point here is that we're going to set our color, our V color that's going to be passed to the fragment shader, right, to 1, 1, 1, 1, 1, which means like white pixel, or rather white vertex attribute, I should say. And then next up in the pipeline, as illustrated here, we have our fragment shader with the color being passed into it, and we see that all it's doing is taking the color that was given to it by the vertex shader and just saying, okay, that's the color of my pixel. That's it. Not doing anything. That's another pass-through shader. All right. So what does this give us? So once the steps in the pipeline have executed, right, following a call to draw, I'm calling it simple draw here because it's more of an example. So I just wanted to show you how that works. So first step, right, we're going to use the program. So if you remember when we initialized, that's where we basically tell OpenGL, okay, those shaders I've configured, time to use them now. Then we pass data to those shaders. So we already have our handles, right? We have our variables into which we're pushing the data. So we're bridging the gap between the two again. All right, so we pass our projection matrix, or transform matrix, sorry. And then we also pass vertices and normals in a big bunch, right? And then the last call here, draw arrays. So we're just basically drawing a number of, and then we're giving it the number of vertexes in there, vertices in there. And you might notice that the first parameter, GL triangles, is us telling OpenGL, so I'm passing you all these vertices and their triangles. It could have been triangle strip if our information was configured differently, but they're not. We were trying to keep things simple. Well, I didn't mention this, but obviously at the bottom here, you see the result of this. It's a white square, white cube, actually, what we're facing in our demo program. All right, oops, oh, yeah, one of those, sorry. All right, basic lighting. So yeah, I'm trying to fly through a lot of this stuff, so you can come and ask me questions after if you're kind of like, you went a bit faster, what the hell was that? So basic light model, if we use the shader as we've configured them right now, this is what we're gonna get when we're gonna rotate our cube in space. Not exactly great. What we want is this on the right. So we need to have a minimum of lighting in there for our scene to do any kind of sense. And we're not going to go beyond minimum because there's ways of, that rabbit hole is pretty deep and pretty awesome, but you know, we want to get somewhere today. So how do we get to this? We need a light source. We're hard coding it in the shader here, but, and then you can see that at the very top, right? So the U-light pos right there. But you can also note how we apply the UMV matrix here, not MVP. So there's an important little distinction here that you'll see in the example code. It's because you want to put that light in 3D space, not projected on screen, right? Because you're still sort of working in the theoretical model. So you want to put all the points in space at the right place, right? So you're taking that light, you're putting it here, and you want it to be sort of moved relative to the camera, etc. But you don't want it projected on screen because you're still at the step where you're calculating theoretical stuff, right? You're not yet in screen space. So that's why the projection part is not there. All right. So our point light source. Point light source, one point emits rays in all directions, right? All right. Transforming the vertex into ice space. So we're applying the same model view transform to our vertex and our normal because all these three things alongside, I mean, with the light source, right, are going to be used in the calculations to find out what color we should be giving our vertex. Right. Then the way to find that out, we get a light direction vector from the light source, right, to the vertex. So we find out what that vertex is, that vector is. Then we calculate the famous Lambert factor. So that's actually very, very simple, right? We just want the angle between the normal and the light vectors, and having that angle allows us to determine what kind of shade we're going to give to that surface. The 0.1 at the bottom, actually, you might wonder, so the actual finding out of the angle is the dot product we see there. So that dot method, being called with model view normal and light vector, that's the one that calculates the angle. And the max part with the second parameter being 0.1, that's the minimum amount of light that's going to be on the surface. So I talked about ambient light. This is ambient light. And the dot product is the Lambert factor, which is diffusion light. All right. And then we multiply that with the color of the object, right? So if our object is white, we multiply it by white. It's going to give us a varying factor. And we're done. All right. So that running that gave us the screenshot we saw earlier. So let's enable the Cardboard SDK now. Enough flat 3D. We're done. All right. So very simple first thing. This is your layout. You just want a full-on cardboard view that fills out your whole view space. Then your main activity, in this case VR talk activity. So these 3 lines highlighted here are what you need to actually configure your view. So you set VR mode enabled to whatever. In this case, I set it to false, just to show you, what happens when you don't have VR enabled. You're just seeing a plain magic window type thing. And turning it on just gives us a stereo view. So at this point, what's happening is we're calling the draw methods twice for half the screen with different camera perspectives, right? Those 2 eyes. And this is the result. At this point, we can just slip this in a cardboard unit and we're good. We have stereoscopy. Stereoscopy. Wait, anyway, I'll get it one day. Right, so what does this look like? There's 2 parts now. Instead of just having one draw command, we have 2 kind of draw command. On new frame, well, it's not at all a draw command, I should say, but it's being called at every frame. And the idea here is that anything that you wouldn't want to set up twice for both eyes, because it's the same for both eyes, you do that job here. So in this case, if you remember, we talked about the projection cone earlier, right? So this is where we set it. So we do set look at M, and we pass all the parameters. So, wait, no, that's not it. It's the camera position. I'm sorry, I confused things. Wrong frame. Anyway, so at this point, what we're saying is basically, we're setting up our camera based on, well, it is the projection cone of sorts, but anyway, you'll see in a second. All right. And before I miss that, the set light position here would be a place where you could set a moving light source, but we don't actually have that in our current scene. But if we wanted our model to dynamically update, we could do those operations here, because you don't want to run them once for each eye, obviously. All right. So the actual on-draw eye command, where things get a bit more interesting. So first thing that's good to do is just to clear the buffers. So just basically clear the screen so that you don't see the results of the previous operation, the previous frame being rendered, having been rendered. And this is where we set up our viewcom, our frustum. So we find out what the ratio is for each eye, just so that our perspective, like our sort of, we won't get a squished image, right? We do that one call here, and that's what's going to set up our whole cone of view. It's fairly simple. We define right, left, right, bottom, top, near, and far. And then, I'm skipping the nice little things I put to highlight everything. All right. Okay. So calculating the view transform matrix, this is the part where we take the camera position and the eye, basically, and turn it into a view matrix. So that's why we need both, right? So this is the part where you basically, the view is camera. Think of the V matrix as the camera matrix of sorts. So at that point, we have our projection matrix, we have our camera matrix. We know the height and width of our viewport. So geometry, for reasons of its own, uses that. Don't pay too much attention to it. The important parts are the updating of information coming from the renderer, so that you can draw stuff based on the dynamically changing position of the head of the user, right? And then the draw command at the bottom. So we'll get back to what actually happens in the draw command a bit later. Okay, so this is the part where things get a little bit more exciting. So what's the point of all of this, right? So at which point am I starting to experiment and having fun? Because to be honest, the part I'm talking about, all of this, it's kind of the boring bit. Like you want to see things animate on screen. You want to sort of create a world, right? You want to be like creative and fast active and you want to do stuff. You just don't want to poke around. So the problem that we have is that, well, okay, I'll talk about live coding. So we want to set up an environment for live coding. What is live coding? It's not live coding on stage, not today, I'm sorry. Within Wi-Fi and everything, and you'll see I need the Wi-Fi for my little demo. That would not have been a great idea. Live coding is when you have a code build run cycle that is so fast it's basically instantaneous, so that you get instant response as you type out your program. You see what's happening. So this is basically it's fragment shader editor online. So we're basically live editing the shader. You see, as I comment out stuff, like we can see it in action. So here we're just basically varying the amount of color depending on our X and our Y on a simple sine wave. So just poking about very, very quickly, we can experiment and find out how all of this works and get a very good feeling for, oh, so that's what a shader, a fragment shader does, right? And you can come up with ideas. And so that instant feedback loop is super important. And on Android, everybody's painfully aware that an APK doesn't build instantaneously, right? So if you want to get into that world of quick experimentation, you're in trouble. It's not going to work. So this is what we're going to, well, this is what I'm basically showing you today, like how to set that up, because it's not that hard. I'll touch really, really quickly. Oh, I'm kind of short on time, so I'll skip on those and ask me questions after. I'll be able to sort of plug those in. So the basic live publishing tools that we have, I use IntelliJ with Node.js, and it runs a small JavaScript program that I can edit that will actually push my geometry into the viewer unit. So what happens is I have my pipeline configured on my phone, and it's getting live data not from itself, but from the internet. So using Firebase that way, if you've played with Firebase, you know that its response time is almost instantaneous. So I can push my geometry and push my edited shader code straight into Firebase, which broadcasts to however many viewer units are actively subscribed to Firebase. So that's fairly interesting. You might be wondering how to do real-time reconfiguration. This slide is just here to show you it's basically the same thing we did at the initialization stage. You can just do it between frames. So you can just create a new shader and compile it and run it. It also means, well, we're going to get to shaders at this point, right? Because we're talking about shaders. Again, I want it to be very, very clear that vertex shaders, they run a few times for each vertices, and then the pixel shader or the fragment shader is running a ton of times, right? What can we do with this? So the geometry I've been talking about is iterative geometry. So with OpenGL ES3, you get a feature where you can define your shape, and you can actually make a ton of copies of it, changing some attributes of it as you go along. So this is the data structure. I'm skipping a bit over because I want to get to the good bits faster. This is me live editing the geometry in IntelliJ. So I hope I did that fast when I recorded it. I can see it's blinking. Right, so what I'm doing is every time I'm uncommenting a line, I'm rerunning the JavaScript program, which is pushing new geometry to Firebase, which is then coming back to the unit. It's actually my physical unit next to my desk, that's my laptop in this case. So we're just adding new shapes as we go. And we're just uncommenting lines right here. So what you can easily do at that point is start putting for loops in there and creating cubes and creating your own spaces. That's a part we won't get to today, but you can see the possibilities, and you can start experimenting very quickly. Then the other thing that we can start doing is deformation. So I'm just mentioning this to sort of let you know what's possible with the shaders and which ways you can use and abuse the pipeline. So in this case, what we're doing is that it's an example. The link is at the bottom. Again, I'm going to share the slides later. But this is an experiment where you take a sphere, you apply noise to the distance of a vertex to the center of the sphere, and you get a deformation like this. And you can come up with really, really nice effects this way. Like that demo ends up being like an actual exploding ball of fire with like really nice effects, and there's about 20 lines of shader code in there. And this kind of stuff is for WebGL, but it's easily applicable to all that I've shown you today on Android. Right, quickly the fragment shaders. So texture mapping, you probably know what that is. You have a texture, you're mapping it onto a shape, right? So you have to sort of think, oh, who's doing the job of that? It's the fragment shader. Fragment shader is getting all that texture data, and since it's responsible for painting the pixels, it's the one that's going to be looking up those pixels, right, in some cases, and taking them straight from the bitmap and dropping them into the right projected space on those triangles. So where does that become interesting? So you can abuse the fragment shader to do kind of interesting things. So here I'm going to show hopefully quickly, how to abuse it to start rendering geometric shapes that have nothing to do with the actual rendering that we're going to be doing. Oh yeah, and the quick note I wanted to show here is that while I'm editing this, so this is the ACE editor running in a web view, pushing, every time I type a change, it pushes to Firebase, comes back to the viewer unit. And what we were seeing at the bottom here was like PIDCAT, logcat. So we were seeing the PIDCAT output of the compile errors that I'm putting into the web view right here, the Chrome pane. So this allows you to play around with fragment shader, and then in this case, the FPS is red to signal that there's a compile error. You can look at your logs. You see which line, what exactly you did wrong. You start editing, and you fix it really quickly. So that allows you to start experimenting with shaders in a way that you probably would have never done if you were just rebuilding the APK every 10 minutes. Hopefully, we should see the results of this. So I'm going to, I'll just let it run until it's done. So now all of a sudden, we just have like this flat polka dot pattern appearing here. So what's going on? So it's really more of a thought experiment, but I just wanted to introduce the audience to the idea that there's something called distance functions that allow you to sort of play around with flat space. So in this case, we're actually ignoring anything 3D. We're just rendering these circles based on where we are in the rendering pass, because the fragment shader knows where on screen it is. So this allows you to do stuff that's kind of fairly interesting, and this is an example of such. Valve has a really nice research paper where they explain how to use the texture system. Instead of actually applying and sticking a texture onto a triangle, what they do is they take a high-res texture here, like 4K by 4K. They extract out of it a distance field patch, which is another texture, really. But they pass this to your fragment shader, and this is only basically telling the shader, OK, if you're at this point, you're this far away from inside or outside the letter, right? And using that, they basically managed to implement something that looks like vector graphics, but is actually stored in a 64 by 64 bitmap. So that's, or texture, I should say. So this is just to introduce you to the idea that you can, once you start programming your own pipeline, you can do very fancy things. And there's a lot of people who have done a lot of fancy things. And research papers like these, you can actually look up on the internet, and they are very, very self-explanatory. Like, you can apply all of this to your programs in virtual space. This is a quick explanation of the full screen fragment rendering trick. This is, I'm going to not explain it too much, but the idea here is that if you want to draw in flat space and only use the fragment shader, you just need to put up a full surface on screen. Like, you put up 2 triangles that fill up the whole view screen, and you can start playing around with the fragment shader. You might be saying, well, what does that do? Like, what can I do that's kind of interesting with that? And here I'm going to encourage you to go and look at ShaderToy. ShaderToy is a fragment editing website, basically with the WebGL APIs. They abuse fragment shaders in an awesome way, and like not just one awesome way. If you go there, you'll get the source code for all these nice examples. If you actually visit this web page, you'll see that all of these things are animated, and you can just learn from the best and reuse that stuff in your own examples. Like, you can see that there's actual worlds being built here. You might be wondering, how the hell can you do geometry if you're just drawing pixels? Like, how does that work? Like, they're not even putting geometry in these examples. It's like 2 triangles we're looking at. So, well, you're going to have to explore that. Explore something called ray marching, or come see me after. I'll give you the links to the papers, because we're short on time and we won't talk about that. We're actually over time. Oh my God, am I good? Well, kick me out if I'm rambling. All right, so one of the things I want to point out too is, like, do a search for something called 2TC in ShaderToy. This is just to impress everybody. They organized what was called a 2-tweet contest. So the concept of the 2-tweet contest is you have however many characters fit in 2 tweets, and that's how big your shader can be in text-wise. So all these shaders fit within 2 tweets. White spaces and comments don't count. And these are all, again, animated if you just do that search and go look that up. And all this stuff is online, and the shaders are public. So you can learn really interesting tricks. And if you start thinking this way, it's not actually so hard. And I've done a few proof of concepts where you can create, say, 3D fractals and apply the VR angle to it as well. So when you do that, you end up creating spaces that are really interesting to explore. And the major point here is that that's not so many lines of code. Once you grok how this stuff works, you can be hyper efficient and come up with like incredible effects. And you don't have to have a production crew next to you that's paid like hundreds of dollars an hour to come up with all those nice assets, right? You can do it yourself. All right. I'm almost done here. I just wanted to, actually, no, we're skipping over those. All right. VR challenges. I'll take 2 minutes just to sort of overview the small problems with the platform. So cardboard, it's awesome, right? But you might see where I'm going with that. Slightly problematic. That can be a drawback. It's not necessarily only a drawback, but you know. The other thing too, you have to think about when you're designing apps for this, you only have one clicker. In some cases, you don't have one at all. And you have to sort of design for that. That's slightly problematic as well. You can get creative and start doing tilt to exit, right? So that's not a bad idea. So you can take examples from the best apps out there and start implementing them in your own. You have to start thinking about head tracking. It's a super rich source of information. You can do all sorts of very interesting experiments with that. I've heard of a startup that recently got financed in Montreal, and all they do is run the analytics to see where you're looking at in the scene, like where the head tracking is going, what's interesting, and they're going to resell that to advertisers. There's fun stuff you can do there. Immersive audio, if anybody went to the HTC Vive tryout, you know what I'm talking about. It puts you into a scene so much more. The slight con there is that it's cardboard we're talking about. Not everybody's going to take the time to put on headphones just for your app, right? So you have to be a pretty compelling app to actually get somewhere. Some pitfalls of the platform. So it's food for thoughts for designing your own apps again. So some of the things that don't work all that great. Centering and drift. So you can try any cardboard app a long while enough, especially if you have a unit that's strapped to your head. You're going to notice that you start off the game sitting this way, and at some point you're like, wait a minute, I'm sitting to the side, I'm still looking forward in the game, what's going on? And nobody seems to think that maybe there should be some sort of reset sit to center switch, because again, you're sitting in your sofa, right? You can't, your range of motion is basically, well, it's not nil, but it's very, very limited. So what's the solution? You suggest to people to sit in a swivel chair? I guess that works, although it kind of gets tricky if you're alone at home, and where did I put that glass again? Or where's my coffee? Standing up with cardboard, actually, this is why I think it's kind of more clever in the way that they put it than the way they have to hold it, because when you're standing up, you can't just flail around and whack people in the head, right? So that's kind of interesting. The problem there, though, is that your reflex to move is ingrained. Like if you're standing up, I am sure that you're going to drift. For having tried it, I can't help myself. At some point, I just take it off and I'm like, oh, crap, I'm like 3 feet this way. Right, so what else? Guided experiences. So you have, since your audience is captive, you can guide their experience. So these are screenshots from a lot of well-known things, I think, but just to go over them again. So this is from, not field trips, but expeditions. So over here, headphones, no distractions. So that's kind of interesting. If in the case of expeditions, for example, the students wear headphones so that they are not distracted by the others and sort of follow instructions more. And the instructor has like the microphone that can feed into everybody's head, basically, right? You can guide your group. You can point big arrows that, that say where to look at. And what I've just shown you, you should see that I've just given you tools that allow you to publish live to a huge group of people anything you basically want. So there's a pretty powerful combination in there. And again, it's with tools that don't require a big production crew behind you to get to somewhere interesting. The advantages with cardboard, back to reality, is really easy, right? You don't have to strap the thing off your head. Scripting, so like Windy Day with a little mouse there, everybody's probably tried this. It has scripted actions, right? So it's being clever in its use of, okay, the user is actually looking, now I can do something. These are all considerations that you have to look into when you're designing an app. Another thing I'd recommend is there's an actual design pattern app from Google that you should really look at. That's very compelling and has some very clever ideas of where you should go. All right. Yeah, almost done. 2 slides. Yay. I'm a bit over, but nobody hates me, so that's good. Time for an upgrade. So this is the point where you go, okay, cardboard's nice, but I'd like to like a proper sort of set, right? So what can you do? So we have Ion VR, sponsored at the BBQ. I tried their unit, really nice. The production units, I think, should be very promising. Like I'm really looking forward to what they come up with. Probably it's going to be soon. That's when I lose my voice. The Oculus Gear is actually super compelling for having tried it. The big advantage here is that they put the touchpad here so you can interact with your world. So that's very much a must and something very much lacking in Cardboard, like this default sort of platform. I want to interact with the world. The Homido is actually a very good headset as well, and they have an offer for like a Bluetooth remote that can be used, so that for users can be interesting. Android Wear, I'm not sharing this with you yet, but eventually on the example code side, there's going to be a proof of concept I've built with Android Wear, where instead of having to touch your temple, you're going to touch your watch, right? And you can easily feed events, touch events into your Cardboard app when the watch is hooked up. It's actually super compelling. It's got like some interesting dynamics because your hands are sort of trapped when you do this, right? So you sort of lose the risk that the user is just going to flail that hot cup of coffee into the dog or whatever, right? So those are like thoughts. Another thought here is that, well, unless they change it in the recent months, as far as I know, if you sell physical goods from an application, nobody takes a cut. That's true, I believe, from Google Play and the Play Store, the Apple Store. So that can always be interesting if you want your users support Cardboard first, and if you want your users to have the full experience and you can actually upsell them on it, like you could make money that way. So that could be interesting because we all know selling apps is not necessarily an easy proposition sometimes. So that's one factor you could consider, which is what this slide was actually about. So I went ahead there. All right, I'm done. Thank you so much. I appreciate you being here.